Nodal analysis is really just an organized way of doing KCL. And KCL, remember, is just saying that the sum of all the currents exiting a node, exiting every node, is 0. And the steps are first to choose your ground. Choose your ground node carefully because you do not need to do a KCL at your ground node. In fact, you cannot do a KCL at your ground node. If you do a KCL at your ground node, your matrices will not be solvable. So you want to choose your ground node at one of the points where most of the wires come together, since that would otherwise be your most complicated KCL. And then you will label all your unknown nodes with voltages that you want to find, V1, V2, V3, and so on. For every V source, you got to do something. Now, because nodal analysis is KCL, KCL loves current sources. It's easy to figure out how much current is exiting a node if it's a current source pulling the current out of the node. It's set by the current source. Voltages will develop any current necessary to keep that voltage the same. So voltage sources require some work. For every voltage source you have, you're going to reduce one of these unknown sources up here. And the way you reduce it is going to depend on whether or not the voltage source is connected to ground or not.
Wait, when we say reduce, do you mean as in just sort of move it, or do you
exactly?
Okay.
So here's in the case where you've got a voltage source that is attached to ground. And Kyle, that's exactly what I mean. You're going to just simply take that V1 right out of there, because now you know that that voltage is set to 2 volts. It gets more complicated when you've got a voltage source that is not connected to ground. So there's stuff out here that I haven't drawn. And when you do this, so this is how we process a voltage source connected to ground. If the voltage source is not connected to ground, what do we call it? Anyone? What will we transform this into?
Supernode.
A supernode. So when you summed up your voltages here, when you summed up the currents exiting the node, that whole node just goes away. You don't, this is part of the node before, and now after your transform, you don't worry about what that node is because you know what it is. Here, you started off with a node to your left, and you started off with a node to your right. It's completely arbitrary which node you decide to get, which voltage source you decide to get rid of. I'm going to get rid of V2. So if we call this thing V1, and if this is 2 volts, this guarantees that the right side will be 2 volts higher than the left. So this must be V1 plus 2. And then the trick is that this whole thing becomes our supernode. So there's more stuff to the right and there's more stuff to the left. And we're going to sum the currents exiting out of that whole supernode with the understanding that over here, the voltage is V1 plus 2. Let me write that to make it clear, V1 plus 2, and to the left, it's just V1. Now that you've got all your nodes labeled, you can do KCL, and you're going to do it at every node or supernode, and you will never do it at ground. If you do, you'll come up with a set of equations that look solvable but won't be. Last question is, do you have dependent sources? If you have any dependent sources, you've got to add an extra equation. And there's no single rule for what that extra equation is, but the dependent source will add an extra variable to your equation. So you'll need to have an extra equation to solve for the extra variable. And that extra equation is often, but not always, Ohm's law. And then you've just got the matrix and solve it. This is how to do any kind of nodal equation, any nodal solution. If you're doing it with phasors, your very first step will be to convert to phasor domain, convert to the frequency domain, and your very last step is going to be to convert to the time domain. So everything in this middle section here is stuff that everything in this middle section is stuff you've already seen in circuits 1, and now we're just going to add that little extra twist to throw it into the phasor domain. Any questions about the overall approach?
Yeah, I was saying for dependent sources, can you specify what you mean by adding extra equation? I don't remember.
So the question is, if you've got a dependent sources, what does it mean to say this add an extra equation? Philosophically, what it means is that if you've got a dependent source, and let's say it's equal to 3 times some current elsewhere in the circuit. So now you've got this I2 elsewhere in the circuit. If this was V1 and if this was V2, you're going to have to change this into a supernode. The supernode is going to be V1, and then this will be V1 plus 3 I2. And your supernode will look like this. What's the problem is that now, before, without the dependent source, you went from having 2 variables, V1 and V2, down to just having 1. But with a dependent source, you went from having 3 variables, V1, V2, and I2, down to having 2, V1 and I2. So you've got this extra variable. Whenever you have a dependent source that looks like this, that is a current elsewhere or some voltage that you haven't already measured, you're probably going to have an extra variable which is a problem, because when you do your KCL at every node, you might have n nodes, so you'll have n equations. But if you have one dependent source, you'll now have still your n nodes. You'll still have n nodes, but you're going to have n plus 1 variables. And you've only got n equations. Without dependent sources, you had n variables. And you've got n equations because you've got n nodes. And you can directly solve for using a matrix equation. But if you got one dependent source, you're going to have one extra variable. You still only got n equations. Fundamental theorem of algebra says you got to have as many equations as you have variables to solve. So you need to get an extra equation. But how can you get that? Let's say this I2 is defined to be, here's a V3 and here's a V4, and this is a 6 ohm resistor. Then your extra equation is going to be that I2 is equal to V3 minus V4 over 6.
Right, that makes sense.
That's your extra equation. You'll throw that into your matrix, and now finally you've got now n plus 1 equations which match with your n plus 1 variables, and you can solve. Make sense?
Yes, sir.
The only exception is that maybe if you're really lucky, instead of this dependent source looking like 3I2, maybe it looks something like 3V3, where V3 was already is already in your matrix someplace, in which case that's not V3 isn't an extra variable, and you still have n nodes and equations, and you can solve directly. So that's a subtle point. Questions about that?
Yes, sir. I actually had just a more general question about dependent sources.
Sure.
And it says if you had 3V3 in an actual circuit, the dependent source would need to know V3, and then based off of V3.
Yeah, your philosophical question is, what the heck is a dependent source? How can a source someplace know what a current or voltage is someplace totally else? Is that right?
Yeah, pretty much.
Yeah, it's like Einstein's concern over spooky action at a distance. I'm going to keep that spooky action at a distance for now. It will become much more clear later on in future courses in electronics how how a source at one part of a circuit could possibly understand what a current or a voltage is at another part of the circuit. But just because I can't leave well enough alone, I'm going to give you a really rough and hand-waving idea that will come from a future class in electronics. Here's a simplified equation for a MOSFET. And when you get into that chapter, you'll learn it's more complicated than that. But think of this. This is a 3-terminal device. You can think of it as a switch between these two terminals with an insulator here. When there's an electric field applied here, it allows current to flow through. It changes what this intermediate dielectric looks like and allows current to flow through here, whereas no current can ever flow in here. So when this is 0 volts, there's no electric field in here, and it looks like an open switch. But when there's 5 volts here, although still no current flows, it now looks like a closed switch between these two terminals. So it literally is a spooky action at a distance, that there's some sort of electric field that's created here that's not here that allows current to flow. So that's an example of how you can get the spooky action at a distance, how a voltage on one terminal here can affect two totally different terminals that, by the magic of drawing a schematic, we could have drawn these terminals on the right side of the schematic, and we could have drawn this control voltage at the left side of the schematic. Does that sort of, as a very hand-waving thing, make sense?
Yes, sir. I think so.
You'll get a lot more understanding when you take electronics next semester. That class directly builds on this one. And then you'll see how to build. You'll also in electronics be building op amps from fundamental circuit components. And an op amp really is just another example of this spooky action at a distance, isn't it? When you think about what an op amp does, what its output terminal is a dependent function of what's happening at its input terminals.